Okay, well, now we're going to look at continuing what we did. So first I'm going to look at this thing called a standard normal distribution. And what is a standard normal distribution? A normal distribution with a mean of zero, mu is zero, and a standard deviation of 1, sigma equals 1, is called standard normal. Can abbreviate by distribution. So standard normal distribution. Now, well, the z-score is not attached to any distribution. When a measurement is normally distributed and we standardize it, the measurement, and we standardize it using what? Using this formula, the z-score formula, where x is my measurement. Again, this is my measurement. The x meaning from data. Then we have standardized it. And all this value tells us is how many standard deviations my value is away from the mean. That's all what this thing does. Okay. So again, so the z-score is the number of standard deviations away from mean. Okay, so so how are we going to use this? We're going to come over here really quick to I'm going to do a search for this program that we're going to use in this class called GeoGebra, and I'm going to use the one that's on the web. So I'm going to click on GeoGebra, search for GeoGebra. This came up, and what I want to choose is GeoGebra Classic. So I'm going to choose that. Okay. Now, when you first go on here, this should appear, and you'll notice there's choices. What I want is probability. Now, and that's what I'm after. But should you, like, for example, what is this? You might decide to click here. Watch, this will all go away. Boom, it's gone. And you go, where'd it go? So to get it back, click on this 3 lines. This is called the hamburger. Go to view. And what we're going to do is select probability calculator, and then all of a sudden this thing pops up. I don't need the graphics, nor do I need the algebra, so I'm going to deselect those, and that's it. So notice the default right now, when I come over here and choose probability calculator, is this normal distribution shows up. And you'll notice that the mean is a 0 and the standard deviation is 1. So again, what is being displayed here is called standard normal. And what are the values right here? This is a z-score of 1, a z-score of 2, a z-score of 3, a z-score of 4, a z-score of -1. So again, what this is saying is that we're -1 standard deviations below the mean, -2 standard deviations below the mean, -3 means we're 3 standard deviations below the mean. Okay. All right. So let's work through this problem one more time. I'm going to come over here and I'm going to calculate just this one above here. Do I want to do that? Sure, why not? It'll be a good lesson. So how does this work? Let's say that I want to now calculate this, but using this program right here instead of this mnemonic. What I want you to realize is that, again, this number is an approximation. What's going to come out of here is another approximation, but much better. It's going to be the 4 decimal places. And the 68, the 95, 90.7 themselves were just estimates. They're not exact. So this has been rounded. The 95 has been rounded. 99.7 has been rounded, so it has a 68%. So let's say I'm after, again, the z-score being greater than 2. Well, right now, this is set, so it is z-scores. Standard normal is a z-score. So I want to go to the right, like I show in the picture. So you'll notice right now it's showing between two things. What's happening is this, it's hard to see because you can see there's a little highlight here, barely visible. I can barely make the difference, but it's sort of blue versus the gray. But what I want is going to the right, greater than. So I'm going to select that. And you'll notice that I have mine a little backwards. This is variable greater than 2. And the way this is written is number less than or equal to variable. Or if I read from right to left, this is variable greater than -1. Again, but that's only because I'm reading from right to left instead of left to right, which we normally would do in English. Okay, so I click here, and what I'm going to enter is a 2. So that's what I want. And then when I do that, I get my answer. The chance of it, a value, a variable being greater than or equal to 2 is 0.0228. So the answer would be 0.00228. Yep. You'll notice, hey, those two numbers are not the same. You're right, because this one is a better approximation. Like I mentioned, it's like sort of a mnemonic. It gives you a quick approximation without getting into too many details. This gives you a better detail. I can get the computer to give me more decimals accuracy if I wanted to, but I'm not going to do that. Okay, so there is my answer to 4 decimal places. And you can see that it's different from this one. They're close, but not exactly the same. So now we're given a situation in 4. The number of hours light bulb light lasts is normally distributed. So this is an important piece of information. They're telling me the distribution, the number of hours bulb light is normally distributed with a population mean of mu, notice, of 800 hours and a population standard deviation of 40 hours. Okay. So I'm going to write all that information. What I'm given is mu is 800 hours. And I'm going to use both notations just to get you used to it. So this is, again, mu, the population mean, also the expected value. And then I'm giving sigma, the standard deviation, and that's 40 hours. And again, just so you can start getting used to it, there's an equivalent version of function notation for the mean and standard deviation, and we can write this as SDX. Again, you'll see later in the course, we're going to start switching more to this notation than this notation. And again, you may see software, you're going to just have to get used to the fact that the software can give you either of these pieces of notation. So I noticed the SD is for standard deviation. So this is the population standard deviation, and meaning that this variable is the population variable. So the expected value of the population variable is 800. The standard deviation of the population variable is 40 hours. Okay. So next I'm going to draw my picture just to remind myself that this is a normal distribution. And I'm going to draw, and I'm going to put the center for the moment here, and I call this X. I could call it anything I want. I don't have to call it X. There's a number of hours, so I could have called this H if I wanted to. But I'm not going to get too creative at the moment. So I will call this X. So now let's read. But notice first, it's just to get an idea of what's happening. I write my information down, and once I do that, I keep going. Let the random variable X denote the number of hours a bulb lasts. Okay, that's what I call it. Oh God, I used X because that was what I needed to use. And now, what percentage of bulbs last 720 hours or less? Notice when it's asking the area under this curve, what is the area under this curve? Well, again, the area can represent here a relative frequency, a probability, a proportion, percentile, and that was just quoted to me as, a percentage. Okay, so, or a percentage. Okay. So it could mean many ways of expressing this area. But I want it to last 720 hours or less, 720 hours. So now I'm not going to worry about the number of standard deviations, all I care about is to mark this on the correct side of the mean, which is somewhere here. So, right, and I'm not too worried about how far right now, and direction. So it's 720 hours. So this is in hours or less, meaning I want to go in this direction. And this is what I'm after. So that's what I'll draw. So what do I do next? Next, I want to calculate my z-score, the z-score of that number. So I'm going to come over here and use that z-score function. So I enter these values, and notice because I've written everything down, I can just easily find them. So I got negative from 20 to 720 to 800 is 80. And if I actually subtract it, I get negative 80. So again, direction is very important. As to the left, so the z-score should be negative because I'm to the left. So I get a negative 2. Hey, it's the same thing as before. Before, I was looking for 2 or greater. This is 2 or less. So if I use the 68, 95, 98.7 rule, for example, so I'm going to do this 2 ways. If I use 68, 95.7, the chance of getting a bulb to last. So this is the way I want you to write it. Give me the measurement as written. And I'm going to come over here and write it as the same thing. So that measurement, so notice the measurement is in hours. So this is in hours. Now I'm going to turn this into a z-score. So I need to enter its equivalent z-score. So 720 as a z-score is negative 2. And the measurement as a z-score is that. So again, I'm using this to go from the measurement to a z-score. And of course, the answer using 68.9.7 rule is 0.025. Again, using 68, 95, 99.7 rule. And this is actually important. Just something to get used to. In statistics, you're always kind of quoting how you got this value, meaning there's more than one way to getting the value or a measurement or some summary. And it's important to let the reader know how you're coming about that answer. Okay. If I did the same thing using GeoGebra, so I'm going to now use GeoGebra, I will come over here, is to the left. Again, notice I need to make sure that the area thing matches. So I'm looking at my picture, looking at this, it's a match. Enter negative 2 here, hit return, and of course I get the same answer because this whole thing is, as you can see, is symmetric, right? I don't think I mentioned this was symmetric, but this curve is perfectly symmetric on either side, as you can see from the picture there. So again, using the GeoGebra or some kind of technology, 2 4 decimal places, the answer is 0.228. Again, I'm going to write here using GeoGebra. Okay, so let's try another question. So I'm going to finish this one up. So I'm going to say about 2.28% of bulbs will last 720 hours or less. Okay, so let's look at this next question. Again, same thing, the number of hours the bulb lasts, normally distributed. So we all have that information. I'm just going to write it all down really quickly. Just to remind myself. Okay. So, and said before, what am I after? What percentage of bulbs will last more than 700, 840 hours? So I'm going to draw my normal curve. Always do that. Always, always, always. Put again, the center, 800. And what I care about is marking this to the correct side of center. And 800 means 840 or more. So it's in this direction. So what I'm after is this. So what I'm going to do next is, again, I'm going to call this measurement X. Let's find my Z-score. 40 minus 800 divided by my standard deviation of 40. So I get, again, difference here is 40 over 40, and it's 1. Okay. So we just noticed what I'm doing now is basically the next step is I'm giving you a question that has words in it. We have to take all the information and transform them and make sure we're nice and neat. Then we're going to find the Z-score, and then we find ourselves in the same scenario as before. And you're going, oh, is that all we're going to do? No, we're going to take it another step in a minute. So again, what I want to do now is write this out. What's the chance of my measurement being 840 hours or more? This is equivalent to saying my Z-score is 1 or more. And by now we kind of have an idea what this is, but I'm going to use 2 different methods. So in fact, I'm going to use GeoGebra first. So I'm going to come over here and just type in 1, because I'm going that number and right. And notice I chose, notice again, my curve. And notice this curve. Look at the direction of the shading. That's important. That's why you want to draw this picture. Type in 1. Oops, nope, not typing in 1. Let's try this again. Click, 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 click. Select. Type in 1. And what I get is 0.158. So, okay, so that's using that rule. Not rule, sorry. This is using GeoGebra. What would happen if I use the 6895.9.7 rule? Again, what I notice is now this is, if I use that rule, in fact, maybe I'll do a separate part here. And I'm going to write it as a Z-score. So our measurement is 1 or greater. I'm after this part right here. We've already done this once before, but I want a reminder. So because I'm dealing with 1, it would be better if I start thinking about 68%. And again, what I want is that tail. So really, another way of writing this is subtract 100% from the 68%. That's going to give me the 2 tails. So this is telling me what I don't want. Sorry, the 68% is not what I want. I'm going to subtract it from 1 and give me the 2 tails, but I only want one of the tails, so that should be half. So using, again, this rule, that gives me 0.32 divided by 2 and comes out to 0.16. Again, using 68.99, sorry, 68.95, 99.7. Okay. Okay, and notice again, just a reminder of the picture. A different picture here. Did I mess up or something? I don't know what this picture is here for. Already forgot. No, that's correct. Well, let's figure this out. Let's do one more question here. What percentage of bulbs last between 720 and 840 hours? Okay, so now I'm gonna, again, I have my information above here. It's out of camera, but I'm not gonna rewrite it because it's just sitting all above there. But normally I would write it, but this time I'm not going to. But I am gonna draw my picture. Okay, and again, I have to mark my center, 800, and now 720 is, I know it seems far away, so I'm going to draw over here, and 840, I know that was just 1 standard deviation, because we just did that one. Okay, so what we want is between these 2 numbers. So mark, again, that's where I'm after. And I know that one's already and z-score of 1, so I'm not going to calculate that one, but I'm going to calculate the 720 and figure out where I am. Okay, so that's 80 looks like, right? 720, yeah, it's 80. Negative 80. And I'm gonna go, okay, 60, 80. Again, making sure that correct. I'm not gonna have a calculator here, but 60 plus 40, yeah, it should be. Okay. So that comes out to -2. If comes out wrong, please forgive me. I don't know why I'm doubting myself, but I am. I mean, 40 plus 40 is 80. 80 plus 20 is 100. So that gives me to that position. Okay, I'm happy with it. So again, notice again, what we're doing is adding this extra step. Now I'm going to write down here what I was after. My measurement is between these two values. And as a z-score, it happens to be between -2 . Okay. Right. So again, if I draw my picture, well, if I use GeoGebra, let me use GeoGebra now. Notice it's between two numbers, so I'm going to choose this value right here. That shows between two. And notice when I choose this, then you have two choices. I'm going to enter -2, and 1 is the other one, right? Yep, it sure is. So it's already in here. So now it says, okay, what's the chance between -2 and 1? The answer is 0.186. Okay, so this is a better approximation because these are exactly 2 and 1 standard deviation. I could use the 68, 95, 9.7 rule, but again, it is going to come out different. So I'm going to do this really quickly. Again, if I use that rule, I just remind myself that this is 1 standard deviation. So really what I'm after is this in picture form. And we already did that for another problem. Similar, so really what this area here is between 0 and 1 is 0.68 divided by 2, but between 0 and -2, that's going to be 0.95 divided by 2. So again, this is GeoGebra, but using this other rule is just going to be the following. Add those up and you get something that's, in fact, we calculated this a second ago. Yeah, 0.815. Okay. So again, the probability, or the percentage of bulbs, you know, we use probability because we're heading to it, but percentage of bulbs that last between 720 hours and 140 hours is again, if I use the more accurate, it'd be 81.86%. Okay, there we go. All right, we'll do a few more here. So one thing I want to emphasize is that when it is 1 or 2, the answer, note every answer so far has been 1 standard deviation, 2 standard deviations. We could use a 68, 95, 99.7. Okay, unless you're told not to, or you must use it if you're told to do that. because otherwise you'll notice the answers are not the same. So if you were going to use the homework and it says use the 68, 95, 9.7 rule, and then you use GeoGebra, well, the answer is expecting is this one, not that one. So that it would mark incorrect. So be aware that the answers are not the same. All right, so let's get to the last part here. Let's see. I'm going to skip now. Should I do this? I'm going to change this a little bit. Mind right now. So I have the situation, and I'm going to do the following. I'm going to change this to the following. Okay, so I'm going to change that 1.5 to 1.55 volts. Okay, so in order for a 1.5 volt battery to work properly, as a matter of fact, I'm going to do this a little more interesting. It's considered effective. Okay, great. So in order for a 1.5 volt battery, the voltage of the battery must actually exceed 1.5 volts. The voltage for any particular battery varies. Distribution of batteries, voltage for battery make a particular factory vary normally with a population mean of 1.7 volts and a population standard deviation of 0.00 volts. Okay. If a battery has a voltage of less than 1.52 volts, it is considered defective. Okay, but that's going to be the mean. This is going to be the standard deviation. Let the random variable y represent the battery voltage. Okay, so we got a change in variable here. What percentage of the batteries coming out of the factory are defective? So again, defective, what does that mean? That is going to be less than 1.52 volts. So let me mark my measurements. The mean or the expected value is going to be 1.700 volts. The population standard deviation, or again, two different ways of writing this, is going to be 0.100 volts. Okay, great. And is it a normal distribution? Yes, that particular factory, very normally. So again, you got to kind of clue into all these things. Yes, the distribution of battery voltage is normally distributed. So I'm going to draw then this picture and put the 1.7 right smack in the center. Okay, and that's the variable y. Great. So the question is, what percentage of batteries coming out of the factory are defective? So it's defective if it's 1.52 volts or less. So anything coming out of here is all defective. Okay. The question is, what percentage of these batteries are defective? So let me turn into a z-score. So I'm going to go 1.52 minus 1.7 and divide this by 0.1. So I'm also going to go over here and I can show you another program called Desmos. I'm going to show you why I like Desmos. I'm going to use the graphic calculator. The scientific calculator works well too. I'll do the scientific calculator. That's fine. All right, so I got my Desmos. What I want to do is enter that value in. So what I'm going to type in, I'm going to put parentheses just to make this easier on myself. 1.52 minus 1.7, oops, 7. And I'm going to hit the slash mark, the division key. I could hit the division button here, or I can use it on my keyboard, the slash mark. I'm going to click here, and it does the following, and then I'm going to enter 0.1. And then immediately notice it gives me the value on the right. So this should be negative 1.8. So this is voltage, but now this is a z-score. So what that tells me is 1.52 is negative 1.8 standard deviations to the right. That's what it's telling me. Right to the left. Sorry, not the right. Did I say the right? No, to the left of the mean. Great. So now I'm going to come over here and type the following. Okay, I want my value, which is y, to be less than or equal to, let's say, 1.52 volts. Less than, okay, so I'm going to just write it exactly as they wrote it. And that as a z-score is negative 1.8 volts. Okay. Now, notice this is not exactly one standard deviation, nor is it two standard deviations. It's somewhere in between. So all of a sudden, I cannot okay? And maybe this is you should not. Alone, the way I've been showing you the 6899.7 rule, you should not be using. But we don't need to now because really all we cared about it was used to memorize exactly 1, 2, and 3. And give you an idea, when it's greater than 1, what's the chance of it being greater than 1? Well, from memory, I know that it's about 60%. What about 2? From memory, I know that it's 2.5%, approximately. Okay, so you kind of do this enough times and you remember those values. So it gives me an idea. But the reality is now that it's not -1 or -2, I just go directly to computer. So I want the values less. So I click here to the less button. I enter what I want, which is negative 1.8. That's my z-score. So these are now, because this is a 0 and that's a 1, these are all z-scores. I enter my z-score into that, and I can see the answer is 0.0359. So about 3.59% of the batteries will be defective. And of course, this is terrible. What is it that this manufacturer could do? Well, I mean, if they can tighten up that standard, the variability seems high for these batteries, so they should tighten that up. We'll find a way to tighten that up. Okay. Anyway, but that's not here or there. Something else. Let me do the following. Let me do something here. Let me call this. I'm not going to calculate that. I'm going to go 1.933 volts. That's what I'm after. What percentage of batteries will have a voltage greater than 1.933 volts? So again, I'm going to draw my picture. I'm going to use the mean and standard deviation that I'm seeing above in the picture here. So I wrote it once. If I hadn't write it, I would do it again. But I write my 1.7, then I write my 1.933, and what I'm after is this area right here. Okay, so what's the chance of that happening? Well, let me write this out here. First, I'm going to find the z-score of that thing. So we got 1.933 minus 1.7 volts. And divided by 0.1. When I calculate this, what I get is 2.33. So again, notice not two standard deviations, not one, not three, it's somewhere in between everything. So now I'm going to calculate. Again, I'm expecting you to do this, so please be aware. You should be doing this on a quiz or exam or whatever. So I call this y. And again, it's a good idea to mark the variable here, just to remind myself. So now here, 2.33, and I'm ready now to calculate. So again, at this point, all I'm going to use is a computer. I want greater than, I select the right thing here, greater than symbol, and I enter my z-score, which is 2.33. And I see that it's 0.09, oops, 0099. So about 0.99% of batteries. Last longer. So what last longer? Sorry, I'm already confused of what I was computing. Of a voltage of 1.933 or greater. Okay, and that's the meaning of that.